Hello, everyone. My name is Savannah Dorn, and I'm the Thermophysical Lab Manager here at Thermtest. In my role, I work hands-on with a variety of thermoconductivity testing methods every day, supporting customers who rely on accurate measurements for critical applications. Today, I'm excited to welcome you to a webinar we're hosting in partnership with one of our valued customers, Scott Hommerding from Ascentek, titled Building Confidence in Thermoconductivity Fluid Measurements with the THW Method, following ASTM D7896. Ascentek is a company of innovators working at the forefront of electronics cooling systems. Many of their products involve high-power devices where overheating can limit performance or even cause failure. In these applications, liquids are often used as coolants, whether in immersion cooling, liquid loops, or advanced heat exchangers. And knowing the thermal conductivity of those fluids is essential for understanding how effectively they transfer heat. That's why today's topic is so important. Together, we want to show how the Transient Hot Wire method, as defined by ASTM D7896, provides the precision and reliability needed to confidently characterize fluid thermal conductivity. In this session, Scott will cover an introduction to the THW method and ASTM D7896, why this standard is particularly relevant for fluid thermal conductivity testing, and how following ASTM D7896 provides data reliability, repeatability, and traceability in industrial applications. If you have questions at any time, please drop them in the chat or send them to us by email. We would love to hear from you. All right, Scott, take it away.
Thank you, Savannah. Yeah, so the title of the presentation is Building Confidence in These Thermal Conductivity Fluid Measurements, following ASTM D7896 and utilizing the THW instrumentation from Thermtest. So as mentioned, wanted to review the transient hot wire technique and then how ASTM D7896 brings that standardization to how it is measured and run, and then ways that you can actually use data validation throughout your testing to kind of support a lot of the unknowns that someone might run in a research scenario. So to quickly overview the methodology of how this is done, the transient hot wire method is run by using a thin resistive wire submerged in the fluid and then applying a voltage across it. And the goal is that when you apply that voltage and you can maintain and measure the temperature and the change of the fluid that it's immersed in, essentially you can take that and correlate it back to measurements for thermal conductivity, specific heat capacity, and diffusivity. So essentially you are measuring, how well does it pull heat, how well does it hold it before it heats itself up, and then that diffusivity, how it transfers across the body of the fluid itself. And it's been something that's been around for quite some time, at least from a theory and a practicality standpoint. But it really wasn't until the use of ASTM D7896, so that is the method held within Subcommittee D15 on antifreeze and heat transfer fluids, that takes this to a preset way to measure accurately, repeatably, and in an automated fashion. So this method introduces what they call a system, or basically the ability to build in automation or instrumentation to make this analysis and this data acquisition kind of all happen in one nice little package. And so within 7896, you get that standardization, and actually, the image that is used within that method of what a standard setup it looks like is an actual Thermtest instrument as well. So it's been something that's been around, been kind of paved by Thermtest from kind of the start. The way that the method works, it lays out your run parameters and all of the ways to, very accurately run the instrument, but it actually does not do anything as far as some methods of like setting standards or validations or calibration checks. So while knowns that are able to be looked up in databases with NIST or other places, we have found at our company that when you're running unknowns or doing research level work, typically there's nothing necessarily established for your matrix. And so it does kind of start to bring in like, yes, the data is repeatable. It is highly, accurate in our experiences as well, but you don't really have a good feel all the time for like, is this number I'm getting? It's repeatable, but is it, accurate or precise to what I'm actually trying to measure? And the method itself does not necessarily address that. And so typically, what we have done is we've built in our own ways of kind of doing that validation. So we've basically taken two different approaches, and you can do a standard, like check standard analysis, or you can run, kind of everything together. So the graph you see here is actually what we would look at as a pre-post standard check. So it's a mess of data over several runs, over several years that we've completed on both deionized water and ethylene glycol. And that's represented in the colored squares and triangles. And then those red spots are actually NIST identified values, and kind of what we would consider like a known or an accepted value for that temperature, for that fluid, for the thermal conductivity reading. And so one way you can kind of validate what you're getting is to be able to run one of these knowns that are a part of maybe the matrix in your unknown that you are running. And what we've done is we've run it, before and after analysis to kind of bookend, indirectly measuring a known and getting a repeatable value to it gives us that confidence that what was generated on our unknown should be correct or within the realm of possibility, or what we're asking to look at. The second way you can do this is you can also run your knowns along with your unknowns on the same conditions and start to compare them referentially again as well. The goal is essentially you're putting baselines out there, and then you're making sure your data fits where you would expect it between those baselines. And so to look at that, this represents something we've actually done for ASTM workshops and presentations is, we're looking at four things we're looking at. We're looking at a thermal measurement for like applications around battery thermal management and things like that to show, all right, the thermal conductivity of our knowns, right? A group 4 base oil, ethylene glycol, water, and then technically our unknown being 50-50 EG in water. And knowing what we know on the fluid side and some of the thermal dynamics up front is, right, water is your best coolant. Ethylene glycol, when we're doing these battery thermal management fluids, is needed to help support boiling and freeze point protection. And so again, your 50-50 EG in water lies about middle of ethylene glycol and deionized water. And what kind of helps, again, take it to that next level is we actually took a formula and we did a ton of different iterative processes on additive selection. And so, it's kind of an eye chart, but a lot of that data generated here, again, looks really, really where we would expect it. And seeing those baselines and like kind of external checks, it helps us give that confidence of like, it is definitely within where we expected, and we can start to get that full differentiation. And kind of just to zoom in on that middle section again, when we were running specific formulas, we again have that reference point in the middle. We have 50-50 ethylene glycol and water, and then our unknowns are kind of our test formulas. We can tell they do fall within the range, within the realm, but they're probably differentiated by the finite portions of their individual formulas. And we end up trusting this data more and more because we know it's where it should be. And we know that I can run any one of those colored lines a large amount of times, and I should never really have a ton of deviation. And we've even in our own lab, within our research, we've done this type of work where we have looked at things of that nature, where we've ran the same formula on, we made a batch of it, we ran the instrument, we ran across our temperature range, we actually changed it out, we ran it again, we changed it out, we ran it again, and all of our results had less than like a 3% relative percent difference within their own runs on that one unknown. And then you pair that against either that upfront, that pre-post validation, or you put it in with these baselines, and again, you gain that confidence to know that this black line, I have good confidence in the thermal efficiency it has over anything else, including the baseline itself. So in summary, it's an extremely powerful method with D7896, and the THW series of instruments kind of help back that up and allow us to do it in a very clean, automated fashion that links right into, data collection. We have everything right at our fingertips. It's all something that we can do very simply and easily. And then the idea of finding a way to put that level of validation with your knowns and unknowns at the same time help bring the confidence in the data you're generating, especially in a research and development situation or a scenario. And a lot of what people are typically using this for in our space relative to, like I said, things like data centers and battery thermal management and a lot of things around that. And everyone's trying to pioneer a little bit of the unknown or kind of push that, where do we find the next innovation? And so having these tools at our disposal has really helped us very much push things forward, push the envelope a little bit, and differentiate ourselves to our customers and our partners. So once again, Scott Hommerding with Ascentek. My contact information is below as well if anyone ever needs to reach out to me. And thank you, Savannah and Thermtest, for giving me the time.
Certainly. So as we've seen today, accurate fluid thermal conductivity data is essential for industries like electronics cooling, where performance and reliability depend on how effectively heat can be managed. So by adhering to ASTM D7896 and using tools like the THW L1, you can be confident that your measurements are precise, repeatable, and fully traceable. If you'd like to learn more, I encourage you to connect with our team of application specialists or reach out directly to experts like Scott to see how the THW method can support your own cooling and fluid testing needs. On behalf of Thermtest, I'd like to extend a sincere thank you to Scott and the Ascentek team for sharing their expertise today. And of course, thank you all for attending.